Hey, so we now begin a 3-video series on the topic of density. As we continue to study the image that W of n creates, many times we're going to be falling back on the idea of W being dense. What does that mean? Well, not every possible point on the circle is the exact landing place of some integer, n, but when we say W is dense, that means that there aren't any gaps, right? No empty intervals. It's the same property that's shared by, say, the rational numbers on the number line. Not every point on the number line is a rational number, but the rational numbers are dense. They fill out every part of the line fully with no holes. So more technically stated, if we refer to the places on the circle by their argument, which is a word that means the angle, theta, we need to show that there does not exist any interval, a plus epsilon, a minus epsilon, that contains 0 points, right? We don't want that. We sometimes call that kind of interval an epsilon neighborhood centered on A, right? So A is the middle, epsilon is kind of the radius. So A is some arbitrary value, could be anywhere, and epsilon should be thought of as like a very small positive value. Smaller it gets, the harder this is to prove, sort of. So we want to prove it for any epsilon, which includes like an unstated no matter how small. And it's always an open interval, meaning that the boundary points don't count. We're talking about the interior of the interval only. So when you're searching for a point, you have to locate it on the actual inside of the interval, not on the edge. In this video, we want to prove that there's at least one point in there for any values of A or epsilon. And the neat thing is, once you prove it contains one point, then it's easy to show that if any arbitrary interval must contain one point, then actually it contains an infinite number of points, because any interval can be further broken up into any arbitrary number of even smaller intervals, and the same proof would be valid for all those intervals as well, right? Cool. But it's the existence of that first point that needs to be established. How do we know that that's true? How do we know that it's true for any possible interval? In order to put a point in a given place, we have to show that there exists some integer that maps there. And we know that each integer has, prime factors, and they each contribute additively to the argument, the angle theta, that determines the location of the point. So it's a matter of showing that we can build that argument, build that angle, as a sum of the psi functions through the selection of which prime numbers and their exponents that we're going to use, so that when we were to multiply all those prime factors together, we get the value n that then maps to the point we want. So now the first thing I'd like to argue, in order to simplify this a little bit, is that for the purposes of proving density, we can totally ignore the fact that there's two halves to the circle. In other words, we're going to imagine that for all numbers n, we just sum up psi of p to the k, and we have a location somewhere on the top half of the circle, between 0 and pi, okay? Why can we do that? Why do we get to do that? Well, suppose I designated an interval, and I claimed that there was no points there, and then you, in order to defend the density property of the function, went and you found the specific prime numbers that result in the psi values adding up to some value inside my interval. All right? Good job, you did it. But suppose I then said, no, that doesn't work. See, because you confused my interval with its mirror image on the other side of the circle. Maybe you have an even number of primes and my interval's on the bottom half with the odds. Or you have an odd number of primes, but my interval's on the top half with the evens. In either scenario, Did you really fail? Well, no, not really. I mean, this is trivial to fix. You just need to multiply by one more prime to get your point to the correct side of the circle. The only catch is that your current sum is already in this very tiny interval, or rather, its mirror image. So when you multiply by one more prime, you just need to take care that that extra prime doesn't bump your point out of the interval. But you already know that as the primes get bigger and bigger, their impact on theta gets smaller and smaller. And the primes, well, they get, here comes that word again, they get arbitrarily big, meaning that their impact gets arbitrarily small. So no matter how small the space is between your current point and the top end of the range that was specified, there's always a prime big enough that that last extra little bit can fit in there. Okay, so now ignoring the whole top-bottom thing, we're thinking strictly about the sum of the psi function, which is going to give us a value between 0 and pi. And the question becomes, is there anywhere in that range that we can't reach? To help us approach this problem, let's first look at another somewhat similar situation. Binary decimals. That's right. To help us get ready to think this through, we're going to look at the real numbers in the interval from 0 to 1, but expressed in a base 2 counting system. So every digit is either a 0 or a 1. Well, just like the digits in base 10 give place values that are powers of 10, like 1/10, 1/100th, 1/1000th, the digits in binary are powers of 2. And on the right-hand side of the decimal point, that's values like 1/2, 1/4, 1/8, 1/16, and so on. And base 2 has one interesting property that no other base has. In the base 10, we can have a number like 0.45, which means 4 of the amount 1/10 and 5 of the amount 1/100th. But the interesting thing about binary, and the reason that I'm using it for my example, is that the digits can only ever be as high as 1, so there's no repetition of same-sized pieces in the sum. For each power of 2, whether it's 1/2 or 1/64th or 1 over 1024, the sum expressed by the written digits either includes one of them or they don't appear at all. Right? The digit is 1 or 0. And it's the same for our size too, isn't it? We have an infinite variety of different values that we can add together, and no two of them are the same. Now, when it comes to binary decimal numbers, clearly they are dense. After all, no matter what base counting system you're using, you can always represent any real number. Does that mean W is also dense by analogy? Well, not so fast. We still need to prove that. But we can use the powers of 2 to help us think clearly about what it would mean for it to fail. With the powers of 2, if we're trying to add up to some target value, we can think about selecting the parts we need as a sort of algorithm, okay? You start by considering the biggest piece, 1/2. If your target is bigger than that, then you include it. Otherwise, you skip it. Then you consider the next biggest piece, 1/4. If that fits, then 1/4 gets included. But if it's too big, then 1/4 is skipped. And so on down the line. Using this simple algorithm, we include or discard smaller and smaller powers of 2, getting closer and closer to our target, right? Here, 1/8 would be added, and then 1/16 would be up for review, and so on. And sometimes we might get lucky and we land right on the target, but that's not necessary. It's enough that we can just repeat the process forever and achieve our target in the limit. right? That's actually what's happening when any decimal numbers just keep going forever, right? Let's back up a bit. Here's something to notice about binary. Each time we discard a power of 2 because it overlaps the target, so it's too big, the sum of all the remaining powers of 2 just happens to be equal to the size of the piece that we just discarded. That remaining portion drops down, and the algorithm continues, selecting and rejecting as long as needed. But what if the sizes of the pieces were not exactly 1/2 of the previous? If the piece sizes vary differently, the algorithm might fail. And if it did, there's really only one way that it could fail. It's like this. One piece could be greater than the sum of all of the smaller pieces combined. If that happens, an interval appears that cannot be summed to. The piece in question is too big to get us there, and the rest combined are too small. That's not just one way the algorithm fails, it's the only way. And I will prove that to you in a few minutes. But right now, let's just appreciate that it does fail. Once the remaining bank of values drops down to below the target, there's no hope of ever reaching the target anymore. With that in mind, let's think about adding up our psi functions. I'll just continue showing them stacked vertically, even though this is really about values that represent an angle. Suppose we've been given an interval that we want to find a point in. We'll set a target that is, say, the center of the interval. Doesn't matter, but let's pick the center. Now let's describe a very simple algorithm for selecting exponents k for each prime p. The algorithm will run, and the outputs of the psi will be added together in a running total until we get an overall result inside the interval, just like in the binary example. We'll start with the first piece and analyze them in order. So that means we're starting with p equals 2, right? That's the first prime number. We're going to find a value of k for that prime, and then we move on to p equals 3, the next prime number. And the bigger the prime number, the smaller the potential output of psi gets. So we're closing in on the target as we go. We're going to keep track of the running total of the psis, of course, the ones we've collected so far. And we'll also have this bank of future values for the primes that we haven't looked at yet. What's different here compared to the binary decimal algorithm is that we are selecting a k value, which affects the size of psi. In between the running total underneath us and the bank above us, we'll have a range of values that we might get from whatever prime we're currently examining. And that ranges from 0 up to some maximum value depending on which k we choose. Let's call the size of that range the spectrum of p, or psi with a little hat on it. Each prime has a spectrum of possible values. And we know from video 2 that we can sort of think of that as 1 over p squared, only we know it's been rescaled so that the whole thing, fits between 0 and pi. But the rescaling doesn't matter, so maybe we'll imagine that the spectrum of p is 1 over p squared and that the total maximum value at the top is g instead of pi. For me, that just makes it easier to think about. So, naturally, each time we look at a prime number, we want to pick the largest k for which the new running total is still less than or equal to the target. That's the rule. But a lot of the time, even k going to infinity won't be too big. So what do we do then? Well, I'm glad you asked. And before we even look at the algorithm in any more detail, we are going to tackle that little wrinkle by saying my favorite word, arbitrarily. What we're going to do is just pencil in a value of infinity for k, just temporarily. And we'll add the full size of the spectrum of p to the running total, just as if it really was infinity. And we'll just keep going. And when we get to the end of the process, We might have many k's that are indicated to be infinity by the algorithm, but that's fine because if the total at that time is right at the target, which is inside of an interval, and really any point in the interval will do, then we can back off of the target a little bit and choose something slightly less. Now, the amount of space we have to work with in the interval might be, very, very tiny indeed, but it won't be zero. We can select large values of k to replace the infinities, making sure that it doesn't reduce our end result enough to take us out of the interval. And since our selection of k's can be arbitrarily large, then we can get psi arbitrarily close to the full size of the spectrum. And that's as true for the sum of several of them as it is for any individual psi. So because we know the word arbitrarily, we know that there must exist some finite k's that would get us to where we need to be. So we don't need to worry about k being infinity. Let's return to our algorithm. So we've specified a way of selecting p's and k's that might add up to the target value. Sometimes we pencil in infinity, and that's okay. Other times, we see the spectrum of p overlapping the target. So we pick whatever value of k gets us, less than or equal to the target. The bank drops down, and we continue, just like in the binary algorithm. We'll always start with enough space in the bank that it appears possible to reach the target, right? So then we simply need to ask, what kind of situation would make this process fail? Now, I proposed before that there is only one description of failure for this algorithm. Let's talk about that. See if you can follow the logic. The algorithm will produce a set of p's and k's, and we will add up the size of those p's and k's, and that will give us, a number. That number will be one of three things: greater than the target, equal to the target, or less than the target. Can't argue with that, right? If it's equal to the target, then the algorithm didn't fail, so cross that out. If it's greater than the target, you didn't follow the algorithm correctly, because the rule is always pick k's that keep the running total less than or equal to the target. So cross that out. Now, if the result is less than the target, then since we start out with a bank of values that extends beyond the target, there must have been some first moment in which the bank dropped down and the new potential total, including the bank, became less than the target. So you must have this moment where you're selecting the biggest k that you can, but the bank drops below the target anyway, which means, pay attention here, the whole bank fits in between psi of p to the k and psi of p to the k plus 1. That's the only way it can fail. By the bank of future values being less than the size of a single increment of k. But can that happen? What we're going to do now is prove that the bank of future values cannot ever be that small, which means that the algorithm can never fail. And if it can't fail, then we can find a point in any interval that we want, and we can conclude that W of n is dense on the unit circle. I'm going to use a fact. This is a known mathematical result that's called Bertrand's postulate, which states that for any positive integer n, there must be a prime number between n and 2n. Now, another way to say that is, if we have a prime, p sub I, let's say, where the I is the index of the prime, we've ordered the primes, right, in size order, then the next prime after p sub I, which we call p sub I plus 1, must be less than twice p sub I. Okay? Now, we're ignoring the rescaling that occurs in psi, like I mentioned before. So ignoring that, if the spectrum of values for p has the size of 1 over p squared, then the spectrum of values for the next prime, p sub I plus 1, is 1 over p sub I plus 1 squared. That would then be limited at a value where we just sub in 2 p sub I in place of p sub I plus 1. Okay, so we've applied Bertrand's postulate to the size of the spectrum of the next prime, not the one we're looking at. And then we can write that as 1 over 4 times p sub I squared, of course. And that's a quarter of the spectrum of p sub I, right? Because 1 over p sub I squared is the size of the spectrum of the prime that we're currently looking at. So we have that the spectrum of the next prime is greater than 1/4 of the spectrum of p. And of course, the spectrum of the next prime is part of the bank of future values that we're looking at when we're looking at p sub I, right? So we can write that the bank, when we're looking at a certain prime, p sub I, is at least the size of the spectrum of the next prime, and therefore the bank itself is greater than 1/4 of the current spectrum. It's actually bigger than that, but it's at least bigger than 25%, right? So now, in order to have this algorithm fail, at the very least, we need consecutive values of k where the difference between them is greater than 25% of the entire spectrum for that prime. And you can see this is virtually never going to happen, right? Like, think back to video 2. We explored all how psi works, you know. When we first increment k from 0 to 1, we get an increase in psi that's equal to 1 over p times the size of the spectrum. That's the first one. And the increments of k are even smaller after that. So we're comparing the bank, which is now at least 1/4 the size of the spectrum, to an increment of k that is no more than 1 over p times the size of the spectrum. So how does 1 over p compare to 1 over 4? Well, clearly, we don't need to worry about 1 over p being the bigger number here, except when, what? Except when our prime number is either 2 or 3. All right, so we've established that our bank is too big to allow the algorithm to fail, except possibly when p is equal to 2 or p is equal to 3. The bank can be bigger than that, and is going to be bigger than that, but we just have a lower bound, right? And knowing that, you know, g is something like 0.4522 or whatever, well, we can just check by inspection for the values of 2 and 3 that the bank is way bigger than the size of the first increment of k. So write down g equals 0.4522 to start us off. For p equals 2, the whole spectrum is of a size 1 over p squared, as we know. For 2, that's 0.25. The first increment of k is 1 over p of that, or half of that. You get 0.125. And the bank at this point is g minus the spectrum of 2, right? So that gives you a value of 0.2022 roughly. And obviously that's bigger than the first increment, which is 0.125. Since the bank is bigger, that proves that the algorithm cannot fail when prime equals 2. After 2, we move to 3. At that point, the spectrum is 1/9, or 0.1111 repeating. We subtract that from the bank. The new bank is 0.0911. And the first increment of k is 1 over 3 times the size of the full spectrum, or 0.037 approximately, which again is smaller than the bank. And that's everything we needed to check. So again, keeping in mind these values do end up getting rescaled, but that doesn't change their relative sizes, right? Which is all that we care about here. Bertram's postulate takes care of the rest of the primes, so we're done. Since the algorithm, therefore, cannot terminate in failure, it succeeds in approaching a limit that's equal to the target. And even though the sum that we built might be an infinite series of psi of p to the k, let's remember that we only need to get inside of the interval, not all the way to the target. So there's some step along the way that will be close enough with an actually finite set of p's and k's that land you where you want to be. So we have density. But believe it or not, that's just the beginning. So stay tuned for Density Part 2.